quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in. Let the outside world dissolve and gently descend into tonight's world. In the last few decades, we moved from guessing about planets around other stars to counting them by the thousands. Each new discovery adds a point of light to a growing map, and with each point comes the same human question. Could anything live there? But habitable is not a single switch. It is a range of conditions, and it is full of uncertainty. Tonight, we will build a calm guide to known exoplanets by habitability ranking. We will not pretend we can list every world one by one like a phone book. Instead, we will rank them by the factors that matter most for life as we understand it. And we will walk through the best candidates, the near misses, and the worlds that are almost certainly hostile. This is a guided sorting of a huge catalogue into simple tiers, with clear reasons for each placement. Tonight, we go through a guide to known exoplanets by habitability ranking. Begin with a simple truth. We do not yet know which exoplanets actually have life. We do not even know, in most cases, if they have air, oceans, or continents. What we have are measurements: planet size, orbit period, distance from the star type, sometimes mass, sometimes density. Very rarely, hints of atmospheric chemistry. So a habitability ranking is a ranking of likelihood, not a ranking of certainty. It is like looking at a house from the street at night. You can see if it has walls, if it has lights, if it is in a safe neighborhood. You cannot see what is happening inside. Now, to make the ranking fair, we need the key factors. First, the star. A planet can be perfect in size and distance, but if the star is violent, the surface may be stripped and cooked. Small red dwarf stars are the most common stars in the galaxy. They live a long time, which sounds good, but many red dwarfs flare. They throw out radiation that can erode atmospheres. Sun-like stars are calmer on average, but they are less common. Second, the orbit and the so-called habitable zone. The habitable zone is the region where liquid water could exist on a planet's surface, given a reasonable atmosphere. This is sometimes called the Goldilocks zone, but the habitable zone is not magic. A planet can be in it and still be dry, frozen, or poisonous. Third, the planet size and mass. A planet too small may not hold an atmosphere. A planet too large may become a mini Neptune, with deep gas layers and crushing pressure. Many researchers think the sweet spot for Earth-like surfaces is roughly in the range of rocky planets, maybe up to about 1.5 times Earth radius, with caution. Fourth, the planet density. If we know mass and radius, we can estimate density, and that hints whether it is rocky. Fifth, the planet rotation and tides. Many planets around red dwarfs are close to their stars. They may be tidally locked, with one side always facing the star. That does not automatically kill habitability. A thick atmosphere or ocean can move heat around, but it changes the picture. Sixth, the presence of water and a stable climate. We usually cannot see this directly yet, but we can infer climate risks. A planet with high radiation and strong tidal heating may be unstable. A planet with an eccentric orbit may swing between extremes. Now, because the catalogue of known exoplanets is huge, we need an approach. We will rank by tiers. Tier 1 will be the most promising known candidates for life as we know it, based on current data. Tier 2 will be plausible, but with bigger known risks. Tier 3 will be worlds that are interesting scientifically, but unlikely to host Earth-like surface life. Tier 4 will be clearly hostile, like hot Jupiters and lava worlds. And within each tier, we will mention the best known examples. Now, before we begin Tier 1, there is another key truth. The best planet on paper is not always the best planet in practice, because planets around nearby stars are easier to study. We can take better measurements. We can look for atmospheres. So in a guide like this, proximity matters, not for habitability itself, but for how soon we can learn. A world that is less perfect but nearby can become more compelling than a more perfect world far away. Now, step into Tier 1. The most famous nearby candidate is Proxima Centauri b. It orbits the closest star to the Sun, a red dwarf. It is roughly Earth mass, or a bit heavier, depending on the measurement. It sits in a region that could allow liquid water. So why is it not an automatic number 1? Because Proxima Centauri is an active star, flares, radiation, and the planet is close. So the question becomes whether it can hold an atmosphere, and whether it can shield the surface. If it has a strong magnetic field, or a thick atmosphere, or an ocean world, it could still be habitable. But the star risk pushes it from perfect to uncertain. Still, because it is close, it remains one of the most compelling targets. Another Tier 1 group comes from a small star with a famous family, the TRAPPIST-1 system. 7 known planets, several in or near the habitable zone. Planets like TRAPPIST-1e and TRAPPIST-1f are often considered among the best candidates. They are roughly Earth-sized. They get an amount of starlight that could allow temperate climates. The star is a red dwarf, again, with flare concerns. But because the system is well studied, it becomes a testing ground. We can observe these planets transiting, crossing the star face. That makes it possible to study atmospheres with modern telescopes. So TRAPPIST-1e often sits high in habitability discussions, not because it is proven, but because it is both plausible and measurable. Now, another Tier 1 candidate that is often mentioned is LHS 1140b. It orbits a red dwarf, but the star is considered quieter than some. The planet is larger than Earth, but may still be rocky. It receives a level of light that could allow a cool, stable climate. Some models suggest it could have a thick atmosphere, possibly even an ocean. So LHS 1140b is often ranked highly. Now another key world is Ross 128b. Ross 128 is a red dwarf that is relatively quiet. The planet is close in cosmic terms. It may receive a moderate amount of starlight. So it is a candidate for a temperate rocky world. Again, uncertainties remain, but it sits in the high tier. Now, consider Teegarden's star B and C. These are planets around a very nearby red dwarf. They are in the region where temperatures could be moderate. If they are rocky, they are promising. And again, because the system is nearby, we can hope to learn more. Now there are also Kepler-discovered planets that are often called Earth cousins. Kepler 186f, Kepler 452b, Kepler 442b. These are often ranked as promising based on their size and orbit. Kepler 186f is Earth-sized and in the habitable zone of a cooler star. Kepler 452b orbits a Sun-like star and sits in the habitable zone. But Kepler 452b may be larger, possibly a super-Earth. Kepler 442b is often considered a strong candidate in terms of receiving starlight similar to Earth. The problem is distance. These are far. We have less detail, so we can rank them as promising in principle, but less testable. Now, more recent surveys have found planets around nearby stars. TOI 700d is a famous one. It is roughly Earth-sized, and in the habitable zone of a small star. Because the star is relatively nearby and the planet transits, it becomes a prime target. TOI 700e is another in that system, also discussed. Now, we must add one more important point. The habitability zone depends on the atmosphere. A planet a bit farther out could still be warm with greenhouse gases. A planet a bit closer in could still be cool with clouds and ice. So these tiers are not strict. They are rough. Now, we will keep moving through Tier 1, but we must also address the danger of easy labels. When people say Earth-like, they often mean only size and distance. But Earth is habitable because of many linked systems: a stable atmosphere, a magnetic field, a certain mix of gases, a long-term carbon cycle, plate tectonics, possibly water. So, our ranking is only the first pass. Now, in Tier 1, we also include planets that may not be perfect Earth clones but might still host life in different forms. For example, a planet slightly larger than Earth could still have a surface, or a planet with an ocean under ice could still host life. But since your request is habitability ranking, we will focus on surface liquid water possibilities first. Now we step into Tier 2. These are planets that could be habitable, but have bigger known risks. One risk is being too large. A planet might be 2 times Earth radius. It might have a thick envelope of hydrogen and helium. That could create deep pressure layers and no solid surface. K2-18b is an example of a world often discussed. It orbits a red dwarf. It is in a region that could allow water. Some observations have suggested interesting atmospheric features, but it is larger than Earth. It may be a mini Neptune, so it sits in Tier 2, highly interesting but uncertain for Earth-like life. Another risk is the star. A planet may be in the habitable zone, but the star may flare strongly. In those cases, habitability depends on atmosphere resilience. Many red dwarf systems fall into this category. Now, another risk is tidal locking and tidal heating. A planet very close to its star may be tidally locked. If the atmosphere is thin, the night side could freeze. If the day side is hot, it could bake. But if the atmosphere is thick, it might still be stable. So tidally locked planets are not removed. They are ranked lower due to uncertainty. Now there is also the issue of eccentric orbits. A planet that swings closer and farther can have extreme seasons. That can stress climate stability. Now Tier 3. These are worlds that are not good candidates for Earth-like surface life, but they are still important. Many are gas giants, hot Jupiters, warm Neptunes, super-Earths that may be too hot. These worlds teach us about planetary formation. They also may have moons. A gas giant in a habitable zone could, in theory, host habitable moons. We do not yet detect exomoons well, but it is a real idea. So, in a broad guide, we note it. Now Tier 4, clearly hostile worlds, planets that orbit in a few days, temperatures high enough to melt rock, atmospheres stripped by radiation. These worlds are not the ones you look to for life. They are still fascinating, but not habitable in the usual sense. Now, with the tiers explained, we will take a calmer approach for the rest of the night. We will walk through the top candidate list again, but with deeper explanations of why each one ranks where it does, and we will build a simple ranking logic that a listener can remember. Star calmness, planet rocky, temperature moderate, water possible, and nearby enough to study. Now return to Proxima b. If we imagine an Earth-mass planet around a quiet star, it would be a strong candidate. but Proxima is not quiet. So the habitability ranking for Proxima b depends on protection. A magnetic field could help. A thick atmosphere could help. A planet that formed with a lot of water could help. So Proxima b remains one of the best targets, but not the cleanest. Now, return to TRAPPIST-1e. It is often treated as a leading candidate, but it is also close to its star. The star has flare history, and the system is compact. So again, atmosphere and climate models matter. If TRAPPIST-1e has a stable atmosphere, it could be a real temperate world. If not, it could be barren. This is why upcoming observations matter so much. Now, return to LHS 1140b. This planet is larger, but maybe rocky. It might have a thick atmosphere. It might even have a cold climate with a warm region. It sits in a place where water could exist, so it remains high. Now, return to Ross 128b. Quiet star, nearby, likely rocky. These are strong points. Now, to broaden beyond the famous names, we need to address the phrase every known exoplanet. There are thousands. Most are not habitable candidates. Many are large gas giants discovered early, because they are easier to detect. Many are close in hot worlds. So, a true guide to every known exoplanet by habitability ranking becomes a guide to sorting. It is a guide to pulling a small set of promising candidates out of a large set of unlikely worlds. That is what we are doing. Now, to keep this accurate and calm, we will avoid claiming exact ranks like number 1 to number 10, because different studies rank differently. Instead, we will describe the commonly agreed top group, then the next group, and the rest. Now, we will continue, and we will bring in more named worlds that appear often in habitability discussions. Another planet that often appears in the promising lists is Kepler 1659c. It is close to Earth in size. It orbits a red dwarf. It receives starlight similar to Earth. But it is far away, and we have limited detail. So it is promising in principle, but not yet testable. Another is TOI 71b, a more recent candidate that sits in the right region around a small star. Another is GJ 667cc, a planet once ranked highly, though the system has complexity and some uncertainties. Another is Wolf 1061c, often mentioned, though it may be closer to the inner edge of the habitable zone. Another is Gliese 832c, larger and closer in, often considered less ideal. Now notice what is happening. Many of the best candidates are around red dwarfs. That is because red dwarfs are common, and their habitable zones are close in, making planets easier to detect. So our catalogue is biased. We find what we can find. In the future, we will find more true Earth analogues around Sun, like stars. But those are harder. Now, in a habitability ranking, we have to be honest about this bias. A planet around a Sun-like star might be more comfortable for life, but we have fewer. A planet around a red dwarf is easier to detect and study, but may face flare risks. So the best list is a compromise between what is likely habitable and what is measurable. Now, let us define a simple habitability score, not as a real number, but as an idea. A planet scores higher if it is likely rocky, it receives moderate starlight, its star is quiet, it is close enough for follow-up, it has a stable orbit, and it is not too large. Now, we should talk about what too large means. When planet radius rises above about 1.5 to 2 Earth radii, the chance of a thick gas envelope increases. Such planets might still have liquid water, but not necessarily a surface. They could have deep oceans under high pressure. They could have layers of ice that form under pressure. They could be what some call Haitian worlds, with oceans and thick atmospheres. Those could, in theory, host life, but it is less like Earth. So in a ranking for Earth-like habitability, we place those lower. Now think about another factor, the star color. Red dwarf light is redder. Plants, if they exist, might absorb different wavelengths. The day sky might look different. This is not a deal breaker. It is just another difference. Now, a huge part of habitability is atmosphere. An atmosphere depends on many things: planet mass, magnetic field, outgassing, volcanism, impact history, star winds. We rarely know these, so the ranking must remain humble. Now, to make the guide useful, we can split Tier 1 into two subgroups. Tier 1A, nearby, rocky, in or near the habitable zone, with a relatively quiet star. Tier 1B, rocky and in the habitable zone, but around a more active star or with other risks. Now place Ross 128b into Tier 1A, quiet star, nearby, a likely rocky. Place LHS 1140b near Tier 1A, with caution about size. Place TRAPPIST 1e into Tier 1b, because the star is a red dwarf with flare concerns, but the planet is extremely interesting and likely rocky. Place Proxima b into Tier 1b, for similar reasons. Place TOI 700d into Tier 1b, though the star may be calmer than some. Now, we can also mention the TRAPPIST planets beyond. TRAPPIST 1f receives less light. It might be colder, but with greenhouse effects, it could still have regions of liquid water. TRAPPIST 1g is farther out and likely colder. It may be more like a frozen world, so those sit lower. Now, we should also discuss a set of planets that are often called super-Earths. Super-Earth is a name for mass and size. It does not mean Earth-like. A super-Earth could be a rocky world with stronger gravity. It could also be a mini Neptune, so the label is misleading. When you see a super-Earth in a habitability list, you should ask, do we know its density? Do we know if it is rocky? Now, because the topic is ranking, we need to describe what makes some candidates drop. One common reason is that the planet is likely too hot. Kepler found many planets close to their stars. Short periods. High equilibrium temperatures. Those are not good for surface water. Another reason is that the planet is likely too big. Another reason is that the star is extremely active. Now, another subtle reason is the planet age. A system that is too young might be chaotic. A system that is older might be more stable. But again, this is hard to measure precisely. Now, we will do a calm walk through the promising list, as it is often discussed in public science writing. Remember, this is not official. It is a guide. Proxima b, TRAPPIST 1e, TRAPPIST 1f, LHS 1140b, Ross 128b, TOI 700d, TOI 700e, Kepler 180f, Kepler 442b, Kepler 1649c, Teegarden star b, Teegarden star c, and a few others in nearby catalogues. Now, to keep this from becoming a name soup, we will slow down and turn each of these into a simple profile. A profile has star type, planet size, temperature estimate, distance and measurability, and the main risk. Now consider Kepler 186f. Star is cooler than the Sun. Planet is about Earth size. It receives less light than Earth, so it might be colder. If it has greenhouse gases, it could be temperate. But it is far, so it is a promising concept. Now consider Kepler 442b, often considered one of the better Kepler candidates. Receives light that could allow liquid water. Size suggests a rocky or near rocky world. Again, far. So high on paper, low on measurability. Now consider Kepler 452b. It orbits a sun-like star. It is in the habitable zone, but it is larger. It may be a mini Neptune or a super-Earth, so it is less clearly Earth-like. Still, it is a famous example. Now consider TOI 700d. Star is a small, cool star. Planet is roughly Earth size. It transits. It is close enough to study, so it becomes a practical candidate. Now consider Ross 128b. No transit detected depending on the system geometry. That makes atmosphere study harder. But the star is quiet, so it remains interesting. Now consider LHS 1140b. It transits. It is larger, but could be rocky, so it is a prime target. Now consider Teagardens Star B. It is nearby. It may be in a temperate zone, but red dwarf risks remain. Now we should also mention that many habitable zone planets around red dwarfs may have had early periods of strong radiation. Red dwarfs can be very active when young. They can blast planets with energy. This could strip atmospheres early, unless the planet had strong gravity and replenished gases, or formed later, or migrated. So again, the star history matters. Now there is another habitability factor that is often ignored. The planet may have too much water. A water world with no land may not have the same carbon cycle. It may lack certain chemical cycles. It could still host life, but it might not be stable in the way Earth is. So, we do not automatically rank water worlds highest. We rank them as interesting. Now consider the idea of moons. A gas giant in the habitable zone could have a moon with a stable climate. We do not yet have confirmed exomoons, but they could exist. If we ever confirm one, it might become a top habitability candidate. Now let us talk about the far end of the ranking, hot Jupiters. These are gas giants that orbit very close to their stars. They are hot. They are likely tidally locked. They are not habitable for surface life, but their existence taught us that planetary systems can be very different from our own. Then there are lava worlds, planets so close that rock can melt. These are not habitable. Then there are cold giants, large planets far out, not habitable. So most of the exoplanet catalogue belongs to the non-habitable tiers, which means our ranking is heavily top-loaded. A few dozen strong candidates, then a long tail. Now, we will move into the most important concept for a habitability guide, the difference between habitability and biosignatures. A planet can be habitable and still empty. A planet can be not very habitable and still have life in some niche. But if we want to find life, we look for gases that suggest biology: oxygen, methane, ozone. But these can also be produced in non-biological ways, so even biosignatures are hard. Now, the next decade of astronomy will focus on this, measuring atmospheres, measuring climate indicators, and refining rankings. So this guide is a snapshot. Now, for the rest of tonight, we will do a slow descent from Tier 1 to Tier 4. We will describe the top set again, but with more scene and feeling, not to romanticize, to make the map easier to hold in the mind. Imagine a nearby red dwarf star, small, cool, a faint red light. A planet circles close. It might have a day side and a night side. It might have a thick ocean and clouds, or it might be a bare rock. This is the uncertainty. Now imagine a sun-like star farther away, a planet in a long orbit, a year similar to ours, a temperature similar to ours, but distant, only a tiny dim signal in our instruments. This is also uncertainty. So the ranking is not only about which world is best, it is also about which world we can learn about. Now we continue. We will bring in more examples. We will explain why some worlds are demoted, and we will end with a calm summary of the top habitability candidates. Now, A careful guide should also explain what the word known means. A known exoplanet is usually confirmed through one of two main methods. The transit method. A planet passes in front of its star and causes a small dip in starlight. This tells us the planet size. The radial velocity method. The planet tugs on the star and the star wobbles. This tells us a minimum mass. When we have both, we get density. When we have density, we get a clue about composition. Rocky, icy, gassy. Now, a habitability ranking begins by filtering. We filter out the worlds that are almost certainly not surface habitable. Gas giants, very large mini Neptunes, very hot close-in planets. That removes most of the catalogue. What remains is a smaller set. Planets with sizes near Earth. Planets with moderate starlight. Planets around stars that are not too violent. Now the next step is ranking within that set. We ask, how close is the planet to Earth in size? How close is the amount of received starlight to Earth? How quiet is the star? How old and stable is the system? And how close is the system to us? Now let us explore the star factor more deeply, because it is the main reason many candidates fall. Red dwarfs can flare. A flare can blast ultraviolet and X-rays. Over long time, this can strip atmospheres. It can also change chemistry. It can harm surface life. But there are ways around it. A planet could have a thick atmosphere. A planet could have an ocean that shields life. Life could exist underground. So flares do not make habitability impossible. They make it uncertain. Now think about a quiet red dwarf like Ross 128. This star is often described as less active. That is why Ross 128b is interesting. If a planet can sit near a quiet red dwarf, it may avoid the worst stripping. Now think about TRAPPIST-1. It is active, though the details depend on time and measurement. So the TRAPPIST planets remain uncertain, but they are testable. Now, another key star category is K dwarfs. These are stars smaller than the Sun, but larger than red dwarfs. They can be stable. They can live long. They may have gentler flare behavior. Many researchers like K dwarfs as a sweet spot, so planets around K dwarfs can rank high if they exist in the habitable zone. Now, in a ranking, we also consider the planet orbit. A stable orbit in the habitable zone is good. A highly eccentric orbit is risky. A planet that dips in and out may face strong freeze and thaw cycles. That may still allow life, but it adds stress. Now let us discuss the inner edge of the habitable zone. Too close and water can evaporate. A runaway greenhouse can occur. A planet can become like Venus. Hot, high pressure, acid clouds. So planets near the inner edge are ranked lower. Now, the outer edge. Too far and water freezes. But with greenhouse gases, a planet can stay warm. So the outer edge is fuzzy. Now, a guide should also address the false comfort of a single number. Some websites show an Earth Similarity Index or a habitability score. These can be useful, but they can also give a false feeling of precision because the input data is uncertain and because Earth similarity is not the same as habitability. So we keep the ranking as tiers and profiles. Now for the rest of the night, we will do a long, steady sweep. We will start at the top. We will move downward. And we will end with a calm list of the strongest candidates. Begin again with the nearby stars. Proxima Centauri b. If it has an atmosphere, it could be one of the closest potentially habitable worlds. If it lost its atmosphere, it could be a bare rock, so it ranks high but uncertain. TRAPPIST-1e. Earth-sized, temperate light. Transits, possible to study. risk from star activity, so it ranks high. TRAPPIST-1F, a bit colder, still possible, ranks slightly lower. LHS 1140b, bigger, possibly rocky. Transits, quietish star, high rank. Ross 128b, quiet star, nearby. Habitable zone candidate, high rank. Teagarden star, B, nearby. Temperate region, high rank, with red dwarf caution. Toei 700d, Earth-sized. Habitable zone, transits, high rank. Now, beyond the nearby stars, we move to the Kepler catalogue. Kepler 186f, Earth-sized. Habitable zone. Distance makes follow-up hard. High in theory. Kepler 442b, often rated well. Distance, high in theory. Kepler 1649c. Earth size, temperate light. Distance, high in theory. Kepler 4F52b, sun-like star, but size risk, mid to high. Now we move to the uncertain but interesting worlds. K2-18b, possible water, but likely not Earth-like. Tier 2, other sub-Neptunes in the habitable zone. Interesting. Lower rank for Earth-like habitability. Now we move to the exotic worlds, hot Jupiters. These rank low for habitability, but they are important for understanding. Now you might be thinking, how can we call this a guide to every known exoplanet? Because the ranking method applies to every planet. Every planet can be placed in a tier. Most of them fall into the low tiers, because most are too hot, too big, or too gassy. So, in a guide like this, the content is not a list of names. It is a sorting key. Now, to make the sorting key more concrete, we can walk through a few typical planet types. Type 1, hot Jupiter, large, close, very hot, low habitability. Type 2, warm Neptune, medium large, gassy, low habitability. Type 3, super Earth close in, rocky, but too hot, low habitability. Type 4, rocky planet in habitable zone, high habitability. Type 5, sub-Neptune in habitable zone, possible ocean world, mid habitability. Type 6, cold rocky planet, frozen, low surface habitability, but could have subsurface. Now, another factor is the star brightness. A planet that transits a small star creates a bigger signal, so we find those. This is why habitable zone planets around red dwarfs dominate the catalogue. Now we should also talk about the future of this ranking. As telescopes improve, we will see atmospheric spectra. We will measure gases. We will refine the tier. Some top candidates will fall. Some mid candidates will rise. So the ranking is alive. Now, because you asked for a guide, we will end with a calm set of rules that a listener can keep. If you hear a planet name, ask, is it around a quiet star? Is it rocky? Is it in the habitable zone? Is it not too big? Is it nearby enough to study? If the answers are mostly yes, the planet ranks high. If the answers are mostly no, it ranks low. Now, we will gently close with a final sweep of the top tier names, because names help the mind anchor. Proxima b, TRAPPIST-1e, TRAPPIST-1f, LHS 1140b, Ross 128b, TOI 700d, Teagarden star b, Kepler 186f, Kepler 442b, Kepler 1649c, and a few others that shift as new data arrives. And let the stars fade back into distance. Each planet a small possibility, each possibility waiting for better light. The catalogue will keep growing, the ranking will keep changing, and the quiet archive will keep recording. Now, we have to admit something plainly. The promise in this topic is so large that it tempts people to oversell. So the archive will not oversell. A habitability ranking is a careful guess. It is a way to decide where to point telescopes. It is a way to decide what to study first. It is not a claim that a planet is a second Earth. Now, to make the guide fuller and more honest, we will do a longer pass through the key uncertainties that shape every rank. First, planet composition. A planet can have the right radius and still be gassy. A planet can look Earth-sized and still have a deep atmosphere, so density matters. But we often do not have density. This means many candidates are ranked with a question mark. Second, clouds. Clouds can cool a planet by reflecting starlight. Clouds can also warm a planet by trapping heat. So even if a planet receives the same starlight as Earth, its surface could be very different. Third, the planet interior. A planet may need internal heat to keep geology active. Geology can recycle gases. It can stabilize climate. But we cannot see plate tectonics from here. So again, it is a question mark. Fourth, the star history. A planet may be calm today, but if its star was violent early, the planet might have lost its atmosphere long ago. So age matters. Fifth, the orbit tilt and seasons. A planet with extreme tilt could have extreme seasons. This might still allow life, but it makes climate stability harder. Now, because of these uncertainties, different researchers produce different top 10s, but the same names keep returning. Proxima b, TRAPPIST 1e, LHS 1140b, Ross 128b, TOI 700d, Kepler 186f, Kepler 442b. And the reason they return is simple. They are near Earth size. They are in or near the habitable zone, and we have enough data to take them seriously. Now, let us add a deeper note about distance. A planet can be an excellent candidate, but if it is hundreds or thousands of light years away, we are limited. We can measure its orbit. We can measure its size. We can sometimes measure a rough mass, but we cannot send a probe. So habitability rankings also have a practical purpose. They help us choose targets for atmosphere studies. Now we will talk about atmosphere studies, because this is where the ranking will change the most. When a planet transits, some starlight passes through its atmosphere. The atmosphere can absorb certain colors. This creates a spectrum. In that spectrum, we can detect water vapor, carbon dioxide, methane, and other gases. But these measurements are extremely difficult. Signals are small. Noise is large. So we will not get answers for all planets. We will get answers for a few. And those few will become the real top tier. Now, in this guide, we should also mention the idea of the habitable zone for different star types. For a sun-like star, the habitable zone is farther out. The year is longer. Transits are rarer, so it is harder to find and harder to confirm. This is why a true Earth twin around a sun twin is still rare in our catalogue. It is not because they are rare in the galaxy. It is because they are hard to detect. Now, another part of habitability ranking is the idea of false positives. A planet may look like it is in the habitable zone, but it may be a dry desert world, a world with a thick, choking atmosphere, a world covered in ice, a world with no stable water. So again, the ranking is not a life ranking. It is a prioritization ranking. Now, to keep the promise of your title, a guide to every known exoplanet, we can describe the overall distribution of ranks. Imagine a huge list. At the top, a thin layer of planets that are rocky and temperate. Below that, a thicker layer of planets that might be temperate, but are too large or too uncertain. Below that, an enormous ocean of worlds that are clearly not surface habitable. Hot Jupiters, warm Neptunes, close-in super-Earths, frozen distant worlds. Those dominate. So, if you pick a random known exoplanet, it will almost certainly rank low for habitability. That is the reality of our current catalogue. Now, for the listener, This can feel discouraging, but it should not, because the fact that we can rank at all is new, and because the catalogue will change. As missions continue, we will find more small planets. We will find more temperate worlds. We will find more planets around quiet stars. So the top layer will grow. Now let us add more examples that often appear in discussions, but are not always in the first 10. GJ 667 CC, as mentioned. It has been studied and debated. Some analyses suggest it is in a favorable region, but the system has multiple planets, and the signal can be complex. Still, it remains a recurring name. Another is Captain B, once discussed, though later work raised doubts. This is another lesson. Some candidates fall away as data improves, so the ranking is not stable. Now consider planets around the star HD 4307. Some were once proposed as habitable zone candidates. But again, the details and uncertainties matter. Now, rather than chase every disputed name, we keep our focus. Nearby, rocky, temperate. Now, we can also talk about one special kind of candidate. Planets around very quiet, old stars. An old star can provide long, stable time for life to develop, but it can also mean the star is dimmer or has changed over time. So the details matter. Now, another special candidate type is the planet that sits on the edge of the habitable zone and might have a stable climate with the help of greenhouse gases. These worlds could be cold but not dead. They could have ice caps and liquid oceans. They could have thick atmospheres. So, in our tier system, they sit in tier 2. Now a note about ranking language. When we say best, we mean best under a certain definition. Life as we know it, surface liquid water, rocky worlds. If we expand the definition, the list changes. Ocean worlds under ice could host life. Moons of gas giants could host life. High-pressure ocean planets could host life. So, the true life ranking could be broader. But for now, we keep the guides simple. Now, we will do one more gentle pass through the top tier, and we will assign each planet a simple reason. Proxima B ranks high because it is close, an Earth mass, but risky because the star is active. Trappist 1e ranks high because it is Earth-sized and testable, but risky because of red dwarf activity. LHS 1140b ranks high because it may be rocky, transits, and may have a calmer star. Ross 128b ranks high because the star is quiet and nearby. TOI 700d ranks high because it is Earth-sized, transits, and sits in the habitable zone. Kepler 186f ranks high on paper because it is Earth-sized and temperate, but low on measurability because of distance. Kepler 442b, similar. Kepler 1649c, similar. Teegarden's star B ranks high because of proximity and temperate zone, but with red dwarf caution. Now, as a final slow thought, remember that the word habitability is also about time. A planet can be habitable for 1,000,000 years, or for 1,000,000,000. Life needs time. So stable, long-lived systems are precious. Now let the guides settle. Thousands of worlds, a few dozen strong candidates, a handful of very strong targets, and in every case, a quiet reminder. We are at the beginning. Now the stars can dim. The catalogue can close. The ranking can rest. We will take one more long step because the size of the subject deserves it. A guide to known exoplanets also needs to explain how the discovery pipeline shapes the ranking. Early in exoplanet history, we found the easy giants, big planets, close orbits, strong signals. That is why hot Jupiters were discovered first. It did not mean the galaxy was full of hot Jupiters. It meant our tools were tuned to them. Then, as instruments improved, we began to find smaller planets, super-Earths, mini-Neptunes. Then we began to find planets closer to Earth size. So the habitability ranking is also a story of technological progress. Now, modern surveys like TESS focus on nearby stars. Nearby stars are brighter, easier to measure. This is why recent candidate lists include many TOI planets. TESS does not see as far as Kepler, but it sees near. This is good, because near is where we can test. Now, when you hear a planet name that begins with TOI, think new, nearby, potential for follow-up. When you hear a planet name that begins with Kepler, think older catalogue, often far, great for statistics, hard for detailed atmosphere work. Now, the ranking uses both. The Kepler planets tell us that Earth-sized planets in habitable zones exist. The nearby TESS planets tell us which ones we can study first. Now, another important factor is the host star brightness and noise. Some stars have star spots. Some have variability. That makes planet signals harder. It also makes atmosphere spectra harder. So a planet around a quiet, stable star can rank higher because it is easier to read. Now, because this is about habitability, we should address the idea of a planet having an atmosphere at all. A planet close to a red dwarf may be bombarded, but a more massive rocky planet may hold on to gases. This is a trade. More mass can help hold air, but too much mass can make a planet a mini Neptune. So we want a balance. Now, another trade is the planet's surface gravity. Higher gravity can help keep air, but it can also make the atmosphere thicker. It can change weather. It can change the boiling point of water. So again, we do not know. Now let us talk about the most common mistake in public habitability talk. People treat the habitable zone like a guarantee. It is not. It is a starting line. Earth is in the sun, habitable zone. So is Mars, near the outer edge. And Venus is near the inner edge. But Venus is not habitable. Mars is not, at least on the surface. So even in our own system, the habitable zone does not decide the outcome. Atmosphere decides. History decides. Geology decides. So for exoplanets, we should be cautious. Now, because the catalogue is huge, it can help to imagine the ranking as a funnel. At the top, all known exoplanets. Then we filter by size. Rocky-sized worlds. Then we filter by starlight. Habitable zone region. Then we filter by star activity. Then we filter by measurability. And what remains is a small list of the best targets. In practice, that list is on the order of a few dozen, not thousands. Now let us add more detail about a few key candidates, just to make the guide feel complete. TOI 700D, as mentioned, remains a key target because it is transiting. Transiting means we can try to see its air. Even if the air is thin, we can learn. TRAPPIST 1E also transits. This makes it a focus. LHS 1140b transits. This makes it a focus. Proxima b does not transit in our view, as far as we know. This makes it harder. But its closeness makes other methods possible. So it stays high. Now, we should mention why some seemingly good candidates are moved down. If the planet radius is above about 2 Earth radii, the odds of a thick gas layer rise. Those worlds might still be interesting for life, but not Earth-like. So K218b, while famous, is ranked lower for Earth-like habitability. Now, another group of candidates are planets in multiple planet systems. Multiple planet systems can be stable, but they can also be complex. Gravitational interactions can change orbits. So, stability checks matter. Now, another point about red dwarf planets. Even if a planet is tidally locked, it can still be habitable in a special way. Some models suggest a ring of moderate temperature between the hot day side and cold night side. This is sometimes called a terminator zone. If the atmosphere is thick enough, heat moves and the extremes soften. So tidally locked does not mean dead. It means different. Now, another point. Habitability may not require an Earth day length. A longer day could still work. A shorter day could still work. So again, many factors are unknown. Now we end the guide with the quiet reason we do any of this. Because somewhere in that catalogue, there may be a world with oceans, with clouds, with seasons, with chemistry that is not only rock and gas, but life. And we will likely find it the slow way, a better measurement, a cleaner spectrum, a repeated signal, a careful check. So the habitability ranking is a way to aim our patience. Now, let the final image be simple. A telescope in the dark, a star in the field, a planet crossing, tiny and silent, a dip in light, a hint of air, a question held gently. Before we truly end, we should add a few more well-known candidates that often appear in habitability discussions, even if they are not always in the top 5. Kepler 62e and Kepler 62f are often mentioned. They orbit a star cooler than the Sun. They sit near the habitable zone. They are not extremely close, so follow-up is hard. But they are part of the reason scientists became confident that small temperate planets exist. Kepler 69c was once discussed, though later work suggested it might be too hot. This shows again how a planet can move up or down as data improves. Kepler 22b was also famous early on. It is in the habitable zone, but it is larger than Earth, so it is likely not a simple rocky Earth twin. It remains interesting, but not top tier for Earth-like habitability. Now, in the nearby star catalogues, there are also worlds like GJ273b, also called Luyten b in some discussions. It is near, it may sit in a temperate region, and the star is a red dwarf, so it becomes another case of high interest with red dwarf caution. There is also Gliese 667c system candidates, as mentioned. There are also planets around the star HD 8552 that have been discussed in the past. Some of these candidates are debated, so in a careful archive, we treat them as provisional. Now, you might wonder why the guide keeps repeating the same caution. Because the most dangerous mistake in this topic is to turn a candidate into a destination. We are not traveling there. We are ranking light signals. So the correct emotional stance is a quiet curiosity, not certainty. Now, let us make the ranking feel even simpler. If a planet is smaller than Mars, it may struggle to hold air. Bigger than about 2 Earth radii, it may be gassy. So the sweet spot is between small, rocky, and not too large. If the planet receives much more light than Earth, it risks a runaway greenhouse. If it receives much less, it risks freezing. So the sweet spot is moderate starlight. If the star is very active, it risks stripping air. So the sweet spot is a quiet star. Now when all 3 sweet spots align, the planet ranks high. Now we can also say what makes a planet rank low instantly. If the orbit is a few days, it is almost certainly too hot. If the planet is Jupiter size, it has no surface. If the planet is Neptune size, it may have no surface. So most of the catalogue ranks low. Now, we will do a final gentle sorting of the entire known catalogue into 4 statements. Most known exoplanets are in close orbits and are too hot. Many known exoplanets are large and gassy. A smaller number are rocky-sized, but still too hot. A very small number are rocky-sized and temperate. That smallest set is where our attention rests. Now, because you asked for habitability ranking, we should close with an honest ranking headline. The best known candidates are mostly rocky-sized planets in habitable zones around nearby small stars. The most famous include TRAPPIST-1e, TOI 700d, LHS 1140b, Ross 128b, Proxima b, and several Kepler worlds that are strong on paper but far. Now, let those names fade into a softer shape, not as destinations, as markers on a growing map. And with that, the archive closes the file for tonight. One more calm section, and then we will let the night take over. There is a hidden tension in habitability ranking. The planets we can rank best are not always the planets most likely to be habitable. They are the planets we can measure. A quiet sun-like star with an Earth twin is, in some sense, the dream. But it is hard to detect. The orbit is a year. The transit is rare. The signal is small. So our current top tier is filled with red dwarf planets. This is not necessarily because red dwarf planets are the best. It is because they are available to our instruments. So, when you listen to the top list, remember, it is a list of the best known candidates, not the best possible candidates. Now, in the future, missions will change the balance. Better radial velocity instruments will measure smaller wobbles. Future surveys will watch stars longer. And as the catalogues grow, we will find more Earth analogues. So, a guide like this is a photograph of a moving river. Now, another useful way to think about habitability is to separate surface habitability and potential habitability. Surface habitability is what people usually mean. A rocky world, liquid water on the surface, a breathable or at least stable atmosphere. Potential habitability is broader. An ocean under ice, a warm ocean on a larger world, a habitable moon, a planet with life in the clouds. We cannot rule these out, but for ranking, we need an anchor. So we keep surface water as the anchor. Now, one more note about ranking. Many planets have only partial data. We might know radius, but not mass, or mass, but not radius, or orbit, but not climate. So, a planet can only be ranked as strongly as its data. This means some planets are put into a holding shelf, promising but incomplete. Now the Quiet Archive can name that shelf, the waiting shelf. These are worlds we should watch, not because they are proven, because they have the right rough shape. Now, for your mind and for sleep, here is the simplest possible final takeaway. If you ever see an exoplanet headline, ask 3 questions. Is it rocky? Is it temperate? And is the star calm? If yes, it belongs near the top. If no, it belongs lower. Everything else is detail. Now the detail is still beautiful. Thousands of worlds, different sizes, different orbits, different stars. We live in a galaxy that makes planets as a normal act, and we are only now learning to read the pattern. So, the habitability ranking is not only about life, it is about learning what a planet can be. Now, the telescope dome closes. The charts are filed. The night outside is quiet. And somewhere, around a small star, a rocky planet turns. It may be empty, or it may be full. Either way, it is real, and it is waiting. If you want to imagine the habitability ranking as a landscape, imagine a gentle slope. At the top are the rare worlds that look most like Earth in the data. Rocky, temperate, quiet star, nearby. Just below are worlds that are rocky and temperate, but around more active stars. Just below are worlds that are in the habitable zone, but may be too large. Just below are worlds that might have subsurface water. And then, most of the way down the slope, the hot planets, the giant planets, the stripped planets, the worlds that orbit so close that their days are counted in hours. All of those are known, all of those are real, and all of those remind us that the universe does not build only gentle Earths. Now, we can also admit something hopeful. Even if a planet is ranked low for Earth, like surface habitability, it can still teach us. A hot Jupiter can teach us about migration. A lava world can teach us about rock atmospheres. A mini Neptune can teach us about ocean pressure. And each lesson improves the ranking, because a good ranking depends on good understanding. Now, let us close by placing your title in a single, clean sentence. A Guide to Every Known Exoplanet by Habitability Ranking is a guide to sorting the catalogue from a small group of promising rocky temperate worlds down through a vast population of worlds that are almost certainly hostile. And the most promising names today are the ones we can both imagine and measure. TRAPPIST 1e, TOI 700d, LHS 1140b, ROS 128b, Proxima b, and a set of distant Kepler worlds that show the type exists. Now, the file can close, not because the question is answered, because the question is safely stored. The universe will keep making planets. Our instruments will keep finding them, and the ranking will keep evolving. Tonight, we have done the first calm sort. And if you ever want to check a planet quickly, without numbers, you can use a simple mental rule. If the planet name is connected to a very small red star, assume tidal locking is possible. That is not bad. It is just a different climate problem. If the planet is called a super-Earth, assume composition is uncertain until density is known. If the planet is called a mini Neptune, assume it is less likely to have a solid surface. If the planet is a hot Jupiter, assume it is not habitable. And if the planet is described as Earth-sized in the habitable zone, then it belongs on the promising shelf, even if it is far. Now that rule will not make you an expert, but it will keep you from being fooled by headlines. Because the truth is that most of the work is careful measurement, not dramatic announcements. Now let the calm return. A star catalogue, a planet catalogue, a small set of top candidates, and a long waiting list. This is how the search for life begins. The last quiet thought is about humility. When we rank exoplanets, we are ranking worlds we have never touched. We are ranking them from tiny changes in light, a dip in brightness, a wobble in a spectrum line, a statistical fit. It is one of the most careful kinds of imagination humans do, because it is imagination constrained by measurement. So when you hear a world called potentially habitable, hear it as a candidate, a place to look, a file opened, not a case closed. And when you hear a world ranked low, do not hear it as worthless. Hear it as part of the full story of planets. The planets that are too hot teach us what heat does. The planets that are too big teach us what gas layers do. And the planets that are temperate teach us where to hope. Now let the hope be quiet. Let it sit beside patience. And let sleep arrive. And somewhere in the background of all this, our own planet keeps turning. The only confirmed habitable world we know. The only world with proven oceans, proven air, proven life. So every habitability ranking is also a mirror. It shows how rare Earth might be, or how common it might be. We do not know yet. But now we have a method. Find, measure, sort, test, and wait. Now the waiting can be peaceful. The catalogue can grow without rushing. New planets will enter. Old candidates will shift. And slowly, one day, An atmosphere spectrum might whisper something unmistakable. Until then, the ranking is a lantern, not an answer. A small, warm light in a very large dark, enough to guide our attention, not enough to claim victory. Now let the lantern dim, let the numbers blur, let the stars become soft points again, far beyond reach tonight. This was a quiet archive story, where the story ends, sleep begins,